This is project 26007, Passive Energy Thermal Airflow Linkage for Vertical Farm. Uh, this project is for the University of Arizona Biosystems Engineering Department under project lead Brian Little, with team members Karina, Petrea, Ethan, Antoinette, Aiden, and Ray.
For some background information, CEA, Controlled Environment Agriculture, is our future for farming in a more sustainable, efficient, and reliable manner. It allows us to grow crops in a fully controlled environment where the plants can develop. This will be especially beneficial in areas with rougher climates and harsher weather for growing all year round. More specifically, vertical farms are systems where plants can grow in grow bed shelves that are stacked on top of one another, with the environment controlled to fit their needs. The vertical farms that are currently at the SEAC focus on the use of LEDs, grow beds, nutrient solution, and an airflow delivery system.
The Pedal VF original scope was to develop a working prototype to passively harvest waste heat from LED fixtures located in the UAG vertical farm. The heat would be converted into electrical power using thermoelectric generators. This electricity would then be used to power the fan system, which provided airflow to the plants grown in the tiered beds at the vertical farm. Airflow plays a critical role in regulating canopy temperature, reducing localized humidity, and preventing physiological disorders such as tip burn. Our initial design was broken down into 3 subsystems: airflow, thermal, and electrical. The airflow subsystem comprised of a fan, adapter, ducts, and a diffuser. The thermal subsystem comprised of TEGs, or thermoelectric generators, thermal paste, heat sinks, and a TEG LED coupling. The electrical subsystem was made up of a battery, Arduino controller, resistance temperature detector, and battery monitoring system.
After some testing with the fan we selected for our basis of design, it was determined that we would require 8 watts of power for 2 of these to achieve our required airflow.
In order to achieve this 8 watts of power, we were tasked by our sponsor to utilize thermoelectric generators, commonly called TEGs. TEGs are a solid-state device which uses Seebeck effect to convert hot and cold temperature difference into electrical power. Our system utilizes a TEG paired with a heatsink mounted to the cool side of the TEG to further create a temperature differential. In order to mount our thermoelectric generators to the LEDs, we had to machine away the existing integrated heatsink on the LED arrays. To do this, we worked with the BE Fabrication Lab to machine down the lights to be able to mount our TEGs to a flat surface. Later that week, we were able to perform our first test of the power output using 3 different models of thermoelectric generators. The results of this test informed us that it would take 1,500 TEGs to provide sufficient power to the fans, proving that the LEDs were not an effective source of heat. Not only was this over budget, but required more space than we had access to. So, in early November, our project underwent a pivot to a different source of heat energy. Our new project scope was to design, build, and test a solar thermal energy harvesting system that demonstrated an alternative renewable energy solution within the University of Arizona's vertical farm. We would be evaluating the feasibility of using thermoelectric generators paired with a custom solar thermal collector panel, which will be placed outside of the vertical farm. The collector panel is electroplated with black nickel to reduce emissivity and improve thermal absorption. The panel provides heat to the hot side of the thermoelectric generators, which are mounted on the back side of the panel. Heat sinks are attached to the cool side of the TEGs to enhance the temperature differential. The power produced from the TEGs will be stored in a rechargeable lead-acid battery for later use at the UAG vertical farm.
In order to help predict the system performance, a MATLAB simulation was created. This simulation allowed us to input parameters like geographical location, angle, and orientation of the panel, as well as mechanical properties like emissivity, absorptivity, thermal conductivity, along with the thickness of the panel. Along with last year's temperature data sourced from the National Oceanic and Atmospheric Administration, we were able to predict the panel temperature of the front, back, and any distance from 0 to 5 inches away from the back of the panel using this MATLAB simulation. This lets us see what the temperature differential each thermoelectric generator will be experiencing is going to be. We were able to check that the simulation was accurate by using test panels, and taking temperature readings, with only a 2 to 3 degree difference between the simulation and real life. Our first verification test was able to be completed with one of our prototypes, which simply stated that the difference in temperature between the panel and the air needed to be greater than 0 degrees. This test passed successfully.
The aluminum panels are electroplated with black nickel, which provides a dark finish and low emissivity. This allows the panels to capture as much heat as possible while minimizing loss reflected back into the air. The electroplating was a multi-step process. Before beginning, we made sure the panels were clean of dust and oils that would reduce the plating quality by washing them in an alkaline degreaser solution. Then we etched the aluminum with sulfuric acid. Next, we deposited a thin layer of zinc onto the etched metal in a zincate solution. And finally, in an electrolyte solution, we sent a current through nickel anodes and the zincated part, which served as a cathode. The electrolyte solution allowed for nickel ions from the anodes to deposit onto the zincated aluminum, and also contained elements that joined with the nickel ions before deposition, giving the final finish its dark color. After air drying and sanding the shaded side to expose the bare aluminum for our TEGs, they are ready to be mounted.
But before mounting the panels, we first had to construct the frame. Using the dimensions provided by the CAD model, several 2x4s were cut and assembled into the frame using outdoor-rated screws. The rain guards were fabricated by cutting 4-inch PVC pipes left over from the original scope lengthwise and then attaching them to the frame to prevent water from being blown in from the sides or the back during a rainstorm. The panels were then attached with an industrial UV-resistant metal adhesive. With the panel sealed to the frame, we could continue our verification tests. The environmental operations test consisted of spraying the frame, battery, and electronics housing with a hose from various angles to simulate rain. These all passed with no issues, aside from a slight oversight in the battery housing procedure, which allowed water to drip in from the edge of the lid when checking for water intrusion after the test was complete. This was resolved by adding a step in the procedure to dry around the edge of the lid before removing, which allowed the test to pass. Now that the environmental operation test had been completed successfully, we were clear to start finishing assembling the system and adding the TEGs and electronics. First, a layer of thermal paste was put in between the TEGs and the heat sinks, as well as the TEGs and the panel. While installing the TEGs, we were able to complete the battery safety verification, ensuring flow of power to and from the battery would stop if either the battery got too hot or the manual disconnect was pressed. After all of the TEGs were installed, we could then begin wiring them together. With the system complete and fully assembled, we were able to complete the 2 final tests to verify we were able to wirelessly transmit our data, along with hitting the power generation requirement of 8 watts.
With all of the verification tests completed, we successfully accomplished our goal of building and testing a solar thermal collector panel that meets the 7 requirements outlined in the thermal, electrical, operation, and safety subsections.